Hello everyone, welcome back to another video. Today we'll be talking about eigenvalues and eigenvectors. Very important equation in physics. I believe one of the most important behind the Schrodinger's equation, or maybe the Dirac equation. So what does this eigenvalue, eigenvector even mean? Well, I'll just tell you. This is the eigenvalue. And this one, x, so there are two, and this is the eigenvector. So, matrices, this A is a matrix, and I'll denote it by these two subscripts. A matrix is really a linear transformation, so it takes perhaps like a vector, maybe pointing here, and it transforms it, maybe it stretches it and changes its direction. But for eigenvalues and eigenvectors, so from this matrix, there will be some special values where, in fact, after being transformed with the matrix, the vector is only scaled. So instead of being turned, it's only scaled, and I'll show that with a graph later, actually. Eigen, in German, I believe, also means special. So how do we exactly compute this? How do we find the eigenvalues, eigenvectors of a matrix? Well, we can rearrange this equation. We can do A minus lambda times the identity matrix, because lambda needs to be a matrix to do the minusing. And the identity matrix is really just a diagonal of ones, which really doesn't do anything. Multiplied by the x vector, and this should be a matrix as well, x vector, and that should equal to 0. Basic algebra, isn't it? Now, there are two solutions to this equation. This is either x equals 0, so that's possibility number 1, or a minus lambda 1 equals 0. Okay, so actually I forgot to introduce a rule here for non-zero eigenvectors. As you can see here, if the eigenvector, the x, is 0, well then that's very boring. All we need to do, for any matrix, the eigenvector is going to be 0, and that's boring, isn't it? So then we look at this one. If we continue, so this one is ruled out. If we look at this one, then that means A equals lambda I. That doesn't make sense either, because if it's a matrix like we want 3, 2, 2, 3, then lambda times I is really just going to be something like lambda 0, 0, lambda. And that's what A has to be, which is almost impossible for any matrix depicting real life. So the solution to this is that we're going to do, suppose that A minus lambda I has an inverse. Has an inverse. Okay? Then, therefore, x should equal the inverse multiplied by the 0 vector. So, x would therefore equal to A minus lambda I inverse multiplied by 0. But this is because we need to get 0, don't we? And this, as mentioned before, doesn't work. We can't make x 0. So the only way that is possible for this to work is that, therefore, A minus lambda I has no inverse. And this is a very big thing, and I'm going to fold the H here. So for those matrices that do not have an inverse, they follow this particular rule, that the determinant of that particular matrix, we will have A minus lambda I, is going to be 0. And this is called the characteristic equation. Very important equation in engineering maths. Very important. We'll talk more about this some other video, I suppose. So, if we remember how the determinant is, the determinant is just like the area of the change, and so with this we can solve for all lambdas, and then we can solve for all eigenvectors as well. So that's what we're going to try and depict. So what's first? Perhaps I'm going to try and draw a graph for you guys, and then we'll then look at some other examples. So here we have the x-plane, and here we have the y-plane. So I'm going to be using this particular example for the whole video, and that's going to be that a equals 1, 2, 2, 1. So it's a particular matrix transform. So what I'm going to show you is that, let's say I have a particular vector here. This is going to be 0, 1. So then that'll be A. So this is, let's say, V. So then we need A acting on V, which will equal to 1, 2, 2, 1, multiplied by V, which is 1, 0. And how I like to think of it is that, it takes it and it rotates it, so it spins it. So it's 1, 2 now. So what we do, the change, it will mean that it's 1 and then up 2. So then the vector goes up here. So as you can see, it's both stretched and rotated. Now I'm going to come back to this and show you the eigenvalue later. So we are going to try computing the eigenvalues with this equation. So let A equal 1, 2, 2, 1. Then lambda I is going to be equal to lambda 0, 0, lambda. Because if you remember, I equals 1, 0, 0, 1. And this is, if you multiply it, 0 times lambda is going to be lambda. 0. So then we have this. Then if we compute A minus lambda I, then this is going to be equal to 1 minus lambda, 2, because 2 minus 0, 2 minus 0 again, so that's 2, and 1 minus lambda. So this is our matrix, and we're going to compute the determinant of it. Now, I will post some more videos sooner or later about how to calculate the determinant for larger and larger matrices, because it's going to be very hard. But for now, for a 2x2 system, it's just this diagonal multiplied minus this cross diagonal. So this is going to be 1 minus lambda squared, because you have 2 of them and you're multiplying it, minus 2 times 2, which is 4. And this should equal 0. So this is going to be a quadratic. And if I expand it using the identity a squared minus 2ab plus b squared, this is going to be 1 minus 2 lambda plus lambda squared minus 4 equals 0. Now, I'm not going to waste your time on this particular equation. It's simply a quadratic equation. So I'll solve it for you. It's lambda minus 3 times lambda plus 1, 0. And therefore, that means that lambda equals 3 or lambda equals negative 1. So with our eigenvalues, that means that some particular vector is either stretched by 3 or reduced by negative 1. And we need to find which vectors it is. So if you remember, we go back to this particular equation, this one right here. We can substitute x in, and then therefore we can get the answer. So we have 2 lambda values, 3 and negative 1. Well, let's sub in lambda equals 3 first. So that'd be a minus 3I multiplied by x should equal 0. And after this, 3i is going to be 3030. A is 1, 2, 2, 1. So this is going to be 1 minus 3, 2, 2, and 1 minus 3. Multiplied by x equals 0. Now, I'm so sorry for being inconsistent with my vectors and all of that. But what I want you to think of x as is, so this is going to be 2, 2, 2, 2. Oh, sorry, negative 2, negative 2. And this is going to be x and y. So there are two components to it, x and y. And this equals 0. So then what I like to think of it, we can set it up as a simultaneous. And we can get x and y, and we flip it, really. So x and y, if we flip it, then x is concerning the negative 2, y is concerning the 2. So then that means that negative 2x plus 2y equals 0. And that 2x, if we flip it again, minus 2y equals 0. So they look the same. That means x equals y. They're exactly the same, really. And if x equals y, that satisfies this equation, that means we can pick any number. And usually we pick 1 because 1's the easiest. So x, y equals 1, 1, which equals our particular eigenvector. Now, I'm not going to do the other one for your practice. And we're just going to simply graph this and see what's so special about an eigenvector. Let me use a blue pen and get the coordinate system back. So, our vector, as seen here, is 1, 1. So 1, 1 is here. 1, 1, because it's 1 in this direction, 1 in this direction. Now, the matrix transform, we are going to apply this matrix transform. So, we are going to have A times our eigenvector equals 1, 2, 2, 1, and multiplied by 1, 1. So then that means, okay, oh shoot, I'm sorry. So that means, if you remember, 1, 1, it takes it to 1, 2, and 2, 1. Or we can set up the simultaneous again. I'm sorry. So here, we split it. So 1 plus 2 equals 3. And then 1, 1 again. And 1, 2 plus 1 equals 3. So 1, 1 split for this one. This first one, 1 and 2, 1 times 1 and 2 times 1. And the second one, 1 times 2 and 1 times 1. And that's 3, 3. So already we can see that it's already a multiple. But if we plot this, it will go here. So as you can see, the eigenvalue is a scaling constant. So it scales. So through a matrix transform, it only scales it. And this is what makes it so special, because we're going to talk about in later videos about diagonalisation, which means we can change it to a new basis, and it makes it much easier to solve linear differential equations with matrices. And that's what's so important about eigenvectors and eigenvalues. So as a recap, eigenvectors and eigenvalues, they follow this particular equation. The matrix A times an eigenvector equals lambda times x, and lambda is a constant. So we looked at a few different examples and came to the conclusion that it must satisfy the characteristic equation. Determinant A minus lambda I equals 0. And so we had an example, and you can try computing yourself. If lambda equals -1, what's the eigenvector going to be? And then we plotted it, and we saw that the eigenvector and eigenvalue, they merely scale. After a matrix transform, they merely scale, whilst rest, they are deformed and changed. So we are going to be talking about diagonalisation next, which means we are going to, as a quick talk about it, we change it into so that x and y fit into this new one. So the dotted are my new x and y, and every other change that happens, or any other vector that happens in this, is merely going to be this just multiplied by the diagonal of these eigenvectors, and you guys are going to understand that in more detail later. So that's today's video. Thank you, and I hope you understand more about eigenvectors and eigenvalues.